First of all, I am Safal Das Biswas. Congratulations you all for selecting for the camp. I will be taking number theory. So without much talk, let's begin. So number theory. So first of all, I am talking about divisibility. Of integers. Okay. A number A belongs to Z. A not equals to 0. B belongs to Z. We say A divides B. Okay. We say A divides B. Little bit of sound problem, so I just off it. I'll switch off my fan. Okay. So a number a number B is said to be divisible by A if there exists C such that B equals to AC, which is equals to minus A times minus C. So minus A also divides B. Okay. So I'm erasing this part. So the definition of A divides B. So the definition of divisibility of integer is a number A belongs to Z, A not equals to 0, B belongs to Z. We say A divides B if there exists C such that A equals to BC, which is similar as minus A into minus C. So minus A B also. A equals to BC. This is the definition up to divisibility, and the extension is if minus A and minus C can be written as a product of minus, and because minus and minus product with positive, product to positive, and so minus A also divides B. Okay. Now some of the properties. I will mention only few properties. 1. A divides B then implies modulus of B greater than equals to modulus of A. 2. A divides B, B divides C implies A divides C. 3. A divides B, C divides D implies AC divides BD. 4. So what is 4? 4 is A divides B, B divides A. This implies modulus of A equals to modulus of B. Modulus only take positive values. Okay. 5. A divides B and A divides C. This implies for all x comma y belongs to integer, A divides dx plus cy. Okay. So please write down these properties if you are noting in some book or copy, copy. If you are noting down in some copy, then please write it down. If you don't write it, you can just see it. Okay, I am erasing it. Six. if C equals to AX plus BY and D divides A and C doesn't divide and D doesn't divide C, then T doesn't divide B or Y. D doesn't divide B or Y. Okay. Okay. This much. Now we will move on to the division algorithm. The division algorithm. It says that, so theorem, okay, so it says that what it says, okay, let A, P, B two integers B not equals to 0, modulus of A greater than equals to modulus of P, then there exists quotient Q and remainder R, both of which are unique, such that A equals to BQ plus R, where 0 less than equals to R less than B. Okay, where 0 less than equals to R less than B. This is the division algorithm. Okay. Okay. I'm erasing it. If you want to write it down, please pause the video and write it. Okay. If you want to write it down, please pause the video and write it. Okay. Now, basic representation theorem. I'm not writing the statement of the theorem, I'm just clearly mentioning it. Integer x greater than n can be written uniquely as as n to the s, can be written uniquely as the expansion of as minus 1 into the s minus 1 dot NA1 plus A0, where AI lesser than equals to n greater than is less than n, for I equals to 1, 2, 0, 1, 2 dot s, where as not equals to 0. This is the basic representation theorem, and this is called, this x is written as as minus 1 dot a1 a0 base n. This is the base n expansion of this integer x, base n expansion of this integer x. This is called the base n expansion of this integer x, and this is also called n-adic expansion. N-adic expansion. Okay. Greatest common divisor, or GCD. So definition of the GCD, I'm not writing it, I will just tell you. Okay. So the definition of the GCD goes as follows. Okay. If for two integers AB, at least one of which is non-zero, first, if G divides A, G divides B. Second, if for any S divides A, S divides B, D greater than equals to S, then D equals to GCD of AB. GCD of AB, also denoted by AB. Okay. I'm erasing it. Please pause the video and write it down if needed. Now, how to calculate the GCD of two numbers? Calculate GCD. Suppose A, B are two numbers and A greater than B, right? Then A equals to BQ plus R by division algorithm, where 0 less or equals to R less than B. If R equals to 0, then GCD of AB is B. If R not equals to 0, then B equals to RQ1 plus R1, where R1 less than R greater than equals to 0. If R1 equals to 0, then R divides B and R divides A, then GCD of AB is R. If R1 not equals to 0, then R1 equals to R1 Q2 plus R2 plus 0 less or equals to R2 less than R1. If R2 is 0, then GCD AB is R1. So if R1 not equals to 0, if R2 not equals to 0, we can continue this process and ultimately we will get a sequence R greater than R1 greater than R2 greater than Rn is greater than equals to 0. This sequence is decreasing and sometimes it hits 0. So there exists Rn equals to Q, Rn equals to Q Rn minus 1 Qn. Okay, R1 R2 R1 into some S Rn minus 1 Rn some S quotient, and Rn divides everyone. Rn divides B, Rn divides A. You can see that Rn divides Ri for all I. So Rn divides B, Rn divides A, so GCD is Rn. So this is the way to calculate the GCD. Okay. Okay. I'm erasing it. The sequence is decreasing, so it hits 0 after some time, right? That is the reason. Okay. 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 Amazing. Now, okay, I'm taking a chalk. Now, benzoates lemma. Sorry if the spelling is wrong, okay? I'm extremely sorry if the spelling is wrong. So benzoates lemma, it says here exists x comma y belongs to z such that GCD AB is AX plus BY. This is very useful for solving many Olympiad problems and many problems further you go on mathematics as your studies, as your major. So it says that GCD AB is AX plus BY. Okay, that's fine. We say A comma B is co-prime if GCD AB is 1 or there exists x comma y with AX plus BY equals to 1. Then AB will be co-prime. Okay. Okay. That's it. Up to GCD. I'm erasing it. So LCM. Now we'll talk about LCM. LCM, the definition goes as follows. If A divides D, D divides D, if 1, 2, if for any S, A divides S, B divides S, and B lesser equals to S, then B equals to LCM AB or LCM AB, also denoted by this. Okay, this is the definition. Okay, I hope you get that. Okay, so I'm erasing. Okay. Now, important theorem. A theorem says GCD of AB and LCM of AB is actually product A into B, or simply AB, right? So this theorem can be proved by using Benzoate's lemma and all that, but I'm not going to prove the theorem. There is a very simple way using fundamental theorem of arithmetic and prime expansion or prime factorization to prove this. Okay, now I'm going to talk about fundamental theorem of arithmetic, and I will prove this theorem, what I had written previously on the board, that theorem using that. So fundamental theorem of arithmetic. Fundamental theorem of arithmetic. It says that theorem every integer greater than 1 can be written uniquely as the product of prime powers. This is the fundamental theorem of arithmetic. Every integer n greater than 1 can be written uniquely as the product of prime powers. Okay, so I am using this part. Suppose n is an integer, so the theorem says it can be written as a p1 alpha 1, p2 alpha 2, pr alpha r in a unique way. I mean, the product of arrangement doesn't matter. That's not the uniqueness. Uniqueness means this expansion will be unique. This expansion and the factorization. Uniqueness means factorization will be unique. Okay, this is the uniqueness. Okay. Okay, I'm raising it. So, last thing before congruency is, suppose A is actually P1 alpha 1, or P1, P2, P3, P4, Pi are primes. Pi are primes. I forget to mention that, and alpha I are integers. I forget to mention that. I mean, in the expansion n P1 alpha 1 Pr alpha r, alpha I belongs to integer, positive and greater than 0, and Pi belongs to prime number set of prime numbers. Okay. Now the last thing I'm gonna mention is, suppose A is P1 alpha 1, P2 alpha 2, Pr alpha r, and B P1 beta 1, P2 beta 2, Pr beta r, where alpha I, beta I greater than equals to 0, and Pi belongs to prime. Suppose this is the factorization AB, prime factorization of AB. I said that this is unique. This is the prime factorization of AB, but you can extend it to some PR because beta is allowed to 0. If you extend the, you can expand by all primes by allowing the exponent to be 0, right? Okay. You can write it as a product of all primes by allowing these exponents to be 0. Okay, so GCD of AB is actually product for Pi, exponent goes to minimum, alpha I, beta I, R1 to R. Okay, and LCM of AB, product I1 to R, Pi, max of alpha I, beta I. Okay, so using this you can prove that this product is AB. How? I'm using this, so you know what is alpha I, beta I. So I will prove that. So GCD of AB into LCM of AB is actually product over Pi max of alpha I, beta I plus min of alpha I, beta I, and from 1 to R. but this is actually alpha I plus beta I, right? This is actually I runs from 1 to R. Pi alpha I plus beta I. This is actually product Pi alpha I product Pi beta I. This is actually A into B. Okay. So I will be taking competency now. So okay. Congruences. Oh, I think video has a problem. Okay. 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 So congruences. We say A congruent to B mod M for a fixed integer M. This is a congruency notation. We say A congruent to, this is a congruent to notation, A congruent to B modulo M for a fixed integer, for a fixed M belongs to integer if M divides A minus B. So the definition, I will not write the definition on the board, I just speak it. I just telling you, I just speak it, that A congruent to B modulo M for a fixed integer M belongs to, for a fixed M belongs to integer if A divides B modulo, if M divides A modulo B. If A not congruent to B, also denoted by A not congruent to B modulo M, also denoted by, this is also denoted by, or A congruent to A modulo B. This is also the notation. So A not congruent to B modulo M if M not divide A minus B. Okay. 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 So properties. So properties. You can see that A is always congruent to A modulo M. A modulo M. Because M divide A minus A. Okay. 2. A congruent to B mod M. B congruent to C mod M. So this implies A congruent to C mod M. Second property, third property, what is it? A congruent to B mod M. Then B congruent to implies B congruent to A mod M. Okay. Okay. Fourth property, A congruent to B mod M. C congruent to B mod M. Then A congruent to, then A plus minus C congruent to B plus minus C D mod M. Okay. And last property is that, this is not the last property, there are many properties. A congruent to C mod M, B congruent to D mod M, then AB congruent to CD mod M, then AB congruent to CD mod M. Another property 6, which is the last property I will mention. There are many properties though. 6. It says that if A congruent to B mod M, then A to the power k congruent to B to the power k mod M for a k belongs to integer. A, B are all integers. A, B, M are all integers. And in the definition, A, B are also integers. In the definition, A, B are also integers, where M is a fixed positive integer. Okay. However, A congruent to B modulo A to the power k modulo M not implies A congruent to B mod M. This is not true. This is not true. This is not true. This is not true. Okay. Now, okay. CRS, complete residue system. What is complete residue system? So complete residue system says that if there are if M divides some integer A with some remainder R, what are the number of possible remainders R? Number of possible remainders R can be 0, 1, 2, n minus 1. Also denoted by integer M modulo Z, mz. This is the set, this set. So this is called the complete residue system modulo M with a remainder R, where R is the remainder. So number of possible remainders 0, 1, 2, 3, 4. So these are the integer class modulo M. Okay, sorry. So 0, 1, 2, 3, 4, a minus 1 are the possible remainders, and total integer set was partitioned into the remainder class. These are the 0 class, 1 class, 2 class. These are the classes of the remainders. This is 0 is the fiber of the integers that are divisible by m. 1 is the fiber of the integer that leaves remainder 1. 2 bar is the fiber of the integer that leaves remainder 2. You will study later in the group theory that this under plus is a group. This under plus is a group. And the amazing thing, this is an abelian group. Abelian, I guess. 1 plus 2 plus 3. Yeah, this is an abelian group under plus. Under plus. Okay. Okay. So this is called. So this set. This is called Z modulo Z. And the set of remainders was denoted by Zm 1, 0, 1, 2, and minus 1. Okay. So this is the additive group under plus, and Zm 0, 1, 2, 3, n minus 1. Sometimes this is also denoted by Zm. This is also denoted by Zm, and there is no difference. This is also denoted by Zm. There is no difference. So Zm are all the possible remainders on division by m. So this set, all the integers of this set form a CRS, complete residue system modulo m. Okay. Now reduced residue system modulo m. Reduced residue system modulo m. Okay. It's denoted by Z M Z invertible. What is that? This is the invertible set. This is a group under multiplication. It says that A bar belongs to Z such that you see A bar comma M equals to 1. Is it A comma M equals to 1? So this is the invertible class modulo m, and you can see that, or this is also denoted by A belongs to Z such that there exists X such that AX congruent to 1 modulo m. This under multiplication is a multiplicative proof, where 1 is the inverse. Okay. So you can see that. Z for a prime P is 0, 1, 2, P minus 1, and Z PZ invertible is 1, 2, P minus 1. Okay. Now P minus 1. Now phi n equals to number of integers greater than 0 less than p less than n such that phi n equals to cardinality of the set number of integers less than or equals to n less than n such that GCD n comma a. Okay, let me write it. Phi n is called Euler-Totient function. This is called Euler-Totient function. This is the number of integers a such that GCD a comma n equals to 1, a less than n greater than equals to 1. So you can see that phi n by n is the probability. What is the phi n by n? So what is the expression for phi n comma phi n? What is the expression for n? So you can see that phi n by n is the probability that an integer is co-prime to n and divisible by n. Co-prime to n and divisible by n and less than n. So this is actually, so if p, a probability that an integer is divisible by p is 1 by p. So it's not divisible by p is 1 minus 1 by p. So this is actually product for all the probabilities p divided n, right? So this is actually product of all the probabilities such that p divide n. So phi n actually n product p divide n, p is a prime 1 by 2. Prime p divide n, a prime p divide n integer has a probability 1 by p, not divisible by p is 1 minus 1 by p, and the product, taking the product, is p divide n for all prime p divide n is actually phi n by n. So this is actually phi n equals to n p divide n times. From here you can see that phi mn equals to phi n comma phi n if GCD m comma n equals to 1. If GCD n comma n equals to 1. Oh. And phi of p to the power k is p to p into p to the power k minus 1 into p minus 1. This is because is actually p to the power k 1 minus 1 by 2, which is the formula I had just established 2 minutes before. Okay, done. Okay, now if Ax congruent to 1 modulo m, then there exists for A belongs to ZMZ invertible, then there exists X belongs to ZMZ invertible denoted by A inverse, such that A inverse congruent to 1 modulo. Since why this occurs, why this happens, because this under multiplication is a multiplicative group. Okay. Multiplicative group. Okay. So this is the case. Now complete residue system. Now if Ax congruent to, if AC congruent to BC, mod M and D is the GCD, C comma M, this implies A congruent to B mod M by D. This is the result. Okay, B mod A congruent to B mod M by D. Okay. Okay. B mod, right? Okay. What is the meaning? See? Okay. Okay. Suppose Ax congruent to B modulo n, then Ax minus B equals to some m into k for m into y for some integer y. So Ax minus my equals to B. Suppose x0 and y0 is the initial solution of this system, then Ax0 minus my0 equals to B. Then what are the other solution of this system, other integer solution? You can take x dash equals to x0 plus m by d t, and y dash equals to, for every integer t, y dash equals to plus m by a by d t, for every integer t where d equals to gcd a comma m. So d equals to g for d, so x prime equals to x0 m by dt, y equals to y0 a by dt, for d equals to gcd a m, and t belongs to integer. So this is a Diophantine equation, and this Diophantine equation has very many solutions. Okay. Now Chinese remainder theorem, CRT. Chinese remainder theorem said that A1, A2, AK are mutually prime. No, sorry. Let me check. Okay. M1, M2, Mk are mutually prime integers. A1, A2, Ak are integers such that Ai, GCD Ami, Ai equals to 1. Then Ai, X congruent to Bi, and B1, B2, Bm are integers, and B1, B2, Bm are integers, and B1 Bk belongs to integers, and M1, M2, Mk belongs to integers. Okay, let me write it clearly. M1, M2, Mk such that belongs to integer, such that GCD Mi Mj equals to 1 or I not equals to j. A1, A2, Ak belongs to integer with GCD Ai, M equals to 1, Ai, M I equals to 1, and B1, B2, Bk belongs to integer, and M equals to M1, M2, Mk product. Then Ai, X congruent to Bi mod M for I 1, 2, k has a solution X congruent to C modulo M. Imply X congruent to C mod M has a solution. X congruent to C mod M, but C belongs to integer. But it implies X congruent to C mod M has a solution. This is the CRT. First note this one, next note this one, next note this one, next note this one. This implies this as a solution. Euler theorem says that A belongs to integer Z and Z invertible, then A to the power phi n congruent to 1 modulo. This is a Euler theorem. A to the power phi n, one of the Euler theorem. There are many Euler theorems. A to the power phi n congruent to 1 modulo n. That phi n is the Euler quotient function. Phi n Euler quotient function. Okay. So one of the results, if P is prime, phi of P is P minus 1, and Fermat's theorem, this is FLT, Fermat's little theorem. This is Fermat's little theorem 1. So FLT1, so what is FLT1? So phi of P is P minus 1. FLT1 says that A to the power P congruent to A mod P. Okay. This is Fermat's little theorem 1. A to the power P congruent to A mod P. Now, another amazing fact is that suppose A1, A2, A phi n there are 5 n integers which are the complete which form a RRS reduced residue system. Suppose A belongs to Z and Z invertible, then A1, A2, A phi n mod n is equals to A1, A2, A phi n. This is also the complete residue system modulo n. Mod n means each element modulo n. The set modulo n means each element modulo n is A1, A2, A3, A phi n. Some permutation of the element. Some permutation of A1, A2, A3, A phi n. This is the permutation notation. Some permutation of A1, A2, they not invert the permutation. This is A1, A2, A phi n. In some permutation, it's not necessary that AI not congruent, but AI congruent to some AJ mod n. AJ mod n by this function. Okay. Now two last things before ending the lecture is Wilson theorem. Says that if P belongs to prime, if and only if P minus 1 factorial congruent to minus 1 mod P. P belongs to prime if and only if P minus 1 factorial congruent to minus 1 mod P, modulo P. Okay. P belongs to prime if and only if P minus 1 factorial congruent to minus 1 modulo P. Okay, this is the Wilson theorem. Okay. Now, Wilson theorem gone. What is it? Okay. Now, if x square, x belongs to integer, if x square congruent to minus 1 mod m mod p for p is prime, then p congruent to 1 modulo 4. This implies p congruent to minus 1 modulo 4. And P congruent to 1 mod 4, another result 1 mod 4 or something else. Try to see. Wait for a minute. Okay. P congruent to 3 mod 4, then P minus 1 by 2, P minus 1 by 2 factorial square congruent to P minus 1 factorial square congruent to 1 mod P. If P congruent to 3 minus 3 mod 4, then P minus 1 by 2 factorial congruent square congruent to 1 mod. Okay. Now I will talk about primitive root, and this is the last one. So primitive root the integer which have primitive root 2, 4, p to the power k, 2 p to the power k, or p is prime. Belongs to prime, k belongs to integer, positive. Greater than equals to integer, positive. So primitive root, the number for which primitive root exists is m equals to 2, 4, p to the power k, 2 p to the power k. These are the only integers for which primitive root exists. What is the primitive root? If for m there exists a g belongs to z m z invertible such that 1 g to the power 0, g to the power 1 dot dot g to the power phi n modulo n are yes, reduced residue system. E to the power phi n minus 1. So d to the power 0, 0 to the power 1 dot dot z to the power g to the power phi n minus 1 are the appropriate residue system. This is the concept of primitive root. There exists at least one. There exists. So for integers 2, 4, p to the power k, 2 p to the power k, but p is prime, k belongs to a positive integer, only has primitive roots. And there exists at least one g belongs to Theorem invertible, for which g0, z1, z phi n minus 1 modulo m are completely over are RSS. Then g is a primitive root. Then g is a primitive root. Okay. So in this video I am going to talk about quadratic congruencies and quadratic reciprocity law. So quadratic congruencies. Okay. So if we noticed the congruencies in the previous chapter and modulo m and modulo of an integer. So if you have the equation ax squared plus bx plus c, which is congruent to 0 mod p, we can see that if p divides a, then bx plus c, which is congruent to 0 mod p, and we see that this can be solved in our previous congruency linear Diophantine equation and all that. This can be solved, which we saw in our previous video. Okay. So now if p equals to 2 and a naught divides 2, then by parity of odd even, we can still solve ax square plus bx plus c. So we will assume p odd prime belongs to odd prime set. So we will assume p belongs to odd prime set. Okay, and p not divides a. In our later, as we go on in the video. So what we will assume? We will assume p belongs to odd prime set and p not divides. Okay. So ax square plus bx plus c congruent to 0 mod p, or p is prime, and a p not divides a. You can see that 4ax is 4 is square x square plus 4 abx plus 4ac equals to congruent to 0 mod p, right? That means 2ax plus b square b whole square equals to congruent to p b square minus 4ac. So y square congruent to, if this is y and if this is b, then y square congruent to b modulo p. Now you can see that if we solve this equation, if we can solve this equation for y, we can solve this equation with this equation reduced to 2x plus b form. If we reduce to some equation plus minus c mod p, if this is solvable, if solvable, then y square plus minus mod p, then this is actually 2ax plus b, which is congruent to plus minus c mod p. Then we can solve this by linear congruency. By Diophantine equation, we already see that. This can be solved by ax, can be solved by other equations. I mean, linear congruency equation. Linear congruency, ax congruent to b modulo, like that, right? Okay. So the equation, so we deal with the equation x square congruent to a mod p. We say a is the quadratic residue modulo p. We say a is the quadratic residue modulo p if x square congruent to a mod p has a solution. Right? Has a solution. And a is called the non-residue modulo p, non-residue quadratic residue modulo p if x square congruent to a mod p doesn't have a solution. Then a theorem, x square congruent to a mod p has at least two solutions. Have two solutions. Have two solutions. Two solutions. If x a is a quadratic residue, if a is a quadratic residue, if a quadratic residue, then a congruent to p square mod p for 1 lesser equals to p lesser equals to p minus 1. These two. And other, there exists p minus 1 by 2 quadratic residue in this set 1 square, 2 square, p minus 1 by 2 square. That means also there are p minus 1 by 1 by 2 non-quadratic residue. Also there are p minus 1 by 2 non-quadratic residue in the set. Okay, that's it. Now Euler criterion says that A is a quadratic residue if and only if a to the power p minus 1 by 2 congruent to 1 mod p, and A is a non-quadratic residue if A to the power p minus 1 by 2 congruent to minus 1 modulo. So A is a quadratic residue if and only if A to the power p minus 1 by 2 congruent to 1 mod p, and non-quadratic residue if A to the power p minus 1 by 2 is congruent to minus 1 modulo p. Okay. Now legendary symbol it says that A by P equals to A to the power P minus 1 by 2 mod P. That means A by P equals to 1 if A is a quadratic residue modulo P minus 1 if not 0 other words. If not a quadratic residue modulo P and 0 residue P and other words. 0 other words. You can see that this can take only 0 or 1 or minus 1 because 0 cases is really complex or absolute or non-absolute. Okay. So some properties of legendary symbol is A by P, AB by P, A by P, B by P. One property. Second property is the second property AB squared by P is A by P. Okay, third property, if A congruent to B mod P, then A by P equals to B by P. Okay, this is the legendary symbol, and there are many theorems regarding this. It's not possible to tell you people all the theorems or record the lecture of all the videos. It will take too much time. So to reduce the time, I am just explaining the symbols and idea. That's it. Not much. Okay. That's it. So legendary symbol A by P, A by P. Okay. So first, quadratic reciprocity law. The law is, if PQ are distinct primes belongs to prime P not equal to Q, then P by Q minus 1 to the power summation box of AP by Q runs from 1 to wait a minute. Okay, sorry. So okay, madam. Okay, and I'm right. P by Q is common to minus 1 to the power Q minus 1 by 2. Minus 1 by 2. That's for Gauss law for quadratic reciprocity is P by Q by Q by P equals to minus 1 to the power P minus 1 by 2 minus 1 to the power P minus 1 by 2. Wait. Okay. So minus 1 to the power, okay, sorry. P minus 1 by 2 into what? P minus 1 by 2, Q minus 1 by 2, and okay, into Q minus 1 by 2. That's it. So this is the quadratic reciprocity law. It says that P by P legendary symbol of P legendary symbol and Q legendary symbol. So there is furthermore, so this is the end. So there is furthermore like Jacobi symbol. So I requested you people to study it alone. Just study it yourself, because this much knowledge you will be needed to understand all this. So thank you. The lecture is totally complete. Thank you.